In this video, we're going to look at how to convert between representing a point or a vector with Cartesian coordinates and cylindrical coordinates. So note we can go either way. We can go from Cartesian to cylindrical or cylindrical to Cartesian. So in order to help us out, at least with this first type of transform we're going to talk about, I've copied here our figure that we used when introducing our cylindrical coordinate system. Of course, this is going to be helpful because we have our x, y, and z axes that we can relate to our rho, phi, and z as we described with our cylindrical coordinate system. So the first type of transform we're going to talk about is something called a point-to-point transform. And as the name suggests, essentially what we're doing here is we're saying, all right, we have a point that is described using a Cartesian coordinate system. How do we describe that same point using a cylindrical coordinate system? In order to do that, let's sort of look at this figure here and let's sort of draw a simple sort of 2D drawing instead of our 3D drawing. So we can say, and what we're looking to do here is because our z is the same, we want to look at the relationships in our xy plane. So within our xy plane, we can say if we come some distance x from the origin and then some distance y from that, well, the distance from this origin up here to our endpoint is going to be our distance rho. So that's the distance from our z-axis. And so this was x and y. And so by definition as well, the angle that we go through from our x-axis to our rho, sort of our position vector there, is going to be our angle phi. So we can label this angle here as phi. And so now we can use this simple triangle, which is a right triangle, of course, to find relationships between x, y, rho, and phi. So let me just bring this down a little bit so we can see that while we are writing these point-to-point transformations. So let's say first that we have our coordinates in our Cartesian, and we want to find out the rho and the phi and the z for our cylindrical. Well, what we could do is we could say from that right triangle, rho is of course going to be equal to the square root of x squared plus y squared. Our phi is going to be equal to the inverse tangent of y divided by x, opposite over adjacent. And then finally, because our z is the same in both coordinate systems, we just say z is equal to z. So these are the equations we would use if we want to go from Cartesian to cylindrical. Now let's say we wanted to go the other way. Well, we could find x from rho and phi, from x equals rho times cosine of phi. Similarly, we could say y is equal to rho sine of phi, and of course we still just have that z is equal to z. So again, just using basic trig with our right triangle there, but if you do have any questions, please let me know. And so this is if we were going from our cylindrical coordinate system to our Cartesian coordinate system. So the second type of transform we're going to talk about is vector-to-vector transforms. And so again, as the name implies here, we have some vector in Cartesian coordinates or in cylindrical, and we want to go to the other coordinate system. And basically, the way we can find these relationships is we look for the relationships between our unit vectors in the two systems. So I'm not going to go through sort of the derivation of that, but if you're curious as to where this comes from, or if you want to see some more details about that, you can look on pages 33 through 35 in the textbook. And again, we're basically just relating, for instance, we have labeled here in the green our unit vectors for our cylindrical system, and then remember for our Cartesian, we just have u of x, u of y, and u of z. So we're using trig to relate these two things. From that, we get two more sets of equations. So our first set of equation is going to give us as an answer our three components for our cylindrical coordinates, our rho component, our phi component, and our z component. And that's going to be in terms of, so we're going to have some matrix here, which is going to be multiplied by our components from Cartesian. So our x component, our y component, and our z component. And so of course our z component should be pretty obvious. It's going to be, our z component is 0 times x, 0 times y, and 1 times z. So z equals z is basically what that's saying. Now for our first two rows, we're going to have trig identities. So we have in our first row cosine of phi, sine of phi, and 0. So again, we can kind of take this to a 2D in the xy plane because our z is the same. Again, see in the text if you want to see the exact sort of derivation of that. And for our second row, we have negative sine of phi times, and then cosine of phi for our second entry, and 0. So this is the equation we would use if we wanted to go from Cartesian to cylindrical. Now notice if we were to plug in here, we have phi over here in this matrix, but if we really only had Cartesian, of course we would have just x, y, and z. So the way we can get around that is, of course, we could say from our equations up here and our little 2D drawing for our right triangle there, we can say that our sine of phi is actually equal to y divided by rho, but again, rho is part of our cylindrical form, so we could expand that and say that rho is equal to x squared plus y squared square root of that. Similarly, with our cosine phi terms, we can say cosine of phi is equal to x divided by rho, where rho is square root of x squared plus y squared. So kind of supplemental equations there to plug into that box equation above. Now, of course, we can go the opposite way. We can find our Cartesian components, ax, ay, and az from our cylindrical components. So again, we're going to have some 3 by 3 matrix, which is multiplied by our cylindrical components, a rho, a phi, and a z. Again, our z components are the same, so for our third row we have 0, 0, 1. For our first row we have cosine of phi, negative sine of phi, and 0. For our second row we have sine of phi, cosine of phi, and 0. And so this would be if we were going from cylindrical to Cartesian. And when is this going to be applicable? Well, maybe we have certain information in one coordinate system, but our problem has symmetry in a different coordinate system, so we want to transfer that information to the coordinate system that we want to solve the problem in. And after we talk about the transforms between all the different sort of coordinate systems, we're going to look at a couple examples so you can get some practice using these equations. But again, ultimately, you just want to have these equations written down somewhere or somewhere you can reference. You don't necessarily need to remember these or memorize how to derive them or anything like that.